Okay, so we've just done quantile regression. What we're going to do next is sort of change gears just slightly. We're slowly building up towards the generalized linear model, which is really just an extension of a lot of the thinking that we're doing this in these, especially these early classes. We're going to pull it all together a little bit later in the semester. I think it's topic, topic 7 or 8? Yeah, general linear models. So we're going to talk about standard errors next time. But yeah, so for topic 7, we're going to talk about the general linear model, generalized linear model. We call regression general linear model, and that can get confusing sometimes. Do y'all like confusing things? Yeah, so do I. No, actually, one of my life passions is like taking something that feels confusing and making it simple. So what we're doing, so hopefully that happens today. It happens on a good day. So what we're doing is building up some of the intuitive idea for maximum likelihood estimation, and then once we have the basic framework set, we're going to go through I think 3 or 4 different examples in analytical form, and then I think we probably won't get there today, but I have a data example where we're actually going to perform maximum likelihood estimation on like a 42 parameter model, which is going to be a lot of fun. This is actually pretty similar to the soccer example in your checkpoint 1, but we're going to do this using maximum likelihood estimation. What we're doing is setting the stage for the generalized linear model. I'm going to throw in some of the generalized linear model terms, and we're going to talk about some of those extensions. But most of what we're doing today in the second part of class is just talking through the intuition and working through some examples. Okay, how many of you have seen MLE before? Okay, so that's nice. If this feels like review, that's great. So what we've done so far is talk about essentially models that are agnostic of where the errors come from. So OLS, we were minimizing the squared residuals, so it looked like this. We talked about absolute deviation in quantile regression, or asymmetric absolute loss. But in all of these cases, what we did, we sat down and we built an objective function where we didn't need to know, we didn't need to make any claims about where the data came from. What we were doing is building a function to make the predictions, but we were not making claims about the function of the errors or of the data. Right? We were estimating the function, but we weren't requiring there to be a particular error function. What we're doing today is sort of flipping this. The starting place, and these are sort of similar in a lot of ways. We did make claims about the functional form of f, but we're sort of starting from a different place. What we're saying is we're going to be very, very specific at the beginning about the data we're drawing from, which, in some ways, is a different place to start. We're making a claim about the data that's being generated, that we would know it. So with the complete probability model, what we're saying is that we believe that each observation is drawn from a very specific distribution. And we need to make a claim about what that distribution is, that form. What we're going to do in the estimation is then go through and estimate the parameters of that specific model, of that specific distribution. So given the data I observed, what parameter values would make this data most likely to occur? So we're sort of flipping the question a bit. In some ways, it'll feel pretty similar, and as I'll show you, maximum likelihood estimation, MLE, and OLS are generally, like, they give very similar results. But it's sort of a different way of posing the same question. In some ways, you can sort of think about this as being a more ambitious claim. It's more structured. We're proposing the full data generating process. We have some nice things. MLE is asymptotically efficient. So this is the smallest variance you can achieve, like the theoretically smallest variance we can achieve among consistent estimators. You can have smallest variance if you're not consistent. And this gives us these nice things, essentially just like it gives it the standard errors. We can use standard errors for our hypothesis tests, and then it allows us to make nice comparisons between models just right off the bat. But it's similar to what we did with Twitter data. If we get the model, like the distribution wrong, this can really make like what's the right word? I need to restart my thesaurus plugin. Like dramatic errors, right? When we are extra specific, but then that extra specificity is wrong, then the mistakes we make are more dramatic than if we hadn't made those specifics. Okay, so here's a bit of the imports. These are just the standard imports, and then these are the colors that we'll use, and here's the data for the example later. So here's this is the big idea. So last class we were looking at non-linear least squares in quantile regression. Looks like some of this is copied from above. But here we're just essentially structuring the parametric form of the data generating process. And then we're going to construct what we call a likelihood function for the data, which is just going to essentially be the product of the probabilities of seeing any given outcome. And then we're just going to multiply that likelihood across all of our data, all of our observations. Okay. This is the basic idea. We're going to build what we call a likelihood function. So we're going to assume that there's a specific data generating process that we know and that we've specified. The only question is what the parameter values of that process are. So the notation here is the same. We have an outcome variable, yi, coming from a known probability distribution, which is dependent on our observables, so we can see all of these xi's, and then unobservable parameter values for the model. So if this looks familiar, that's because it's the exact same notation that we've been using, or at least similar. Fy is just the data generating process that generates y, and then xi is the observable input data, and then theta is just the vector of parameter values. Here you can sort of think of thetas as our beta parameters in nonlinear least squares. Like all we're doing is really just tuning the function. Okay, so let's walk through a bit of an example and set this up using sort of our more classical regression. So let's say we have something like a classic linear regression. So we have yi conditional on xi. So this is what's our output variable, our outcome variable, given our predictor variables, xi. And let's say this is normally distributed. We have a mean of xi times beta, and then a variance of sigma squared. So all very standard things. You could probably do all of this in your sleep. And in grad school, I would call those nightmares. Best joke all day. The rest of the week is downhill. So the density function, you'll remember this is like the function for the density of the normal distribution. This is just notation. I got lazy and didn't want to write it all out. And then this is just the model. So this is yi minus xi times beta over sigma. So all I'm doing here is just normalizing this. So this on top, it's just the error terms. And then so those would be centered on 0. And then I'm just standardizing it by the standard deviation. And let's say for simplicity here at the beginning, we have 3 observations. The probability of seeing 3 very specific observations is the probability of seeing the first one times the probability of seeing the second one times the probability of seeing the third one. So this is sort of a joint density. These are all probabilities, right, or heights, on our PDF, and all we're doing is just multiplying these together to give us the density of seeing all 3 of them at the same time. Any questions here? This is the first brick in the wall we're building. I don't know if Pink Floyd knows maximum likelihood estimation, but okay. So this is the basic building block. We have the density specifically. And all we're going to do is think about what am I doing here? So let's just say the variance of the error is 1. This is just going to make our model a little bit simpler. So I think the only thing I'm doing here is just making this simpler. If we know the betas, this whole thing just simplifies to this thing. Okay, so the main idea here is we're just going to make our model incredibly simple. The main idea with maximum likelihood estimation is that we're going to focus on this density function, and we're going to try to pick our parameter values simply to maximize it. We want the probability to be as high as possible given our parameter values, with the probability of seeing the data that we see to be as high as possible by choosing our parameter values. That's the entire ballgame. Okay. And all we're going to do, we just have one parameter, beta 0. But because each of these different observations are drawn from the same underlying distribution, each of these 3 models is going to be exactly the same. So the model predicting y1 is the same as the model predicting y2, and is the same as the model predicting y3. And then we're just multiplying them together. Okay. So here's a little example. This is just a likelihood function. And all I'm doing is just, I'm giving it beta 0. And then I have this first element, which is normal PDF. And then I'm going to multiply it by the second one. We have our 3 observations. So we have 1, -1, and 3. And then we're going to plot different beta 0 values and then just see what this looks like. So this is y1, it's 1, and then we're going to subtract off beta 0. So this just gives us our error term for the first model. We haven't picked beta yet, or beta 0. What we're going to do is play around with what beta 0 looks like. What we're doing is just printing out the height of the PDF at whatever error we get. Any questions about this? Just the height of the error at beta 0 for our first observation, which just tells us the likelihood of seeing that observation. And then we just do the same thing for the other two. We're just multiplying each of these together. Okay, so they're all numbers, just 3 functions evaluated at the same inputs on the horizontal axis, and we're just multiplying them together. So I'm going to define this, and then we're going to run this. So this is the likelihood for this thing we just defined. It's a specific set of y values, and we're plotting on the horizontal axis the likelihood function. And you can see there's a peak. And what we're trying to do essentially is build like a analytical apparatus to be able to find this peak. This is essentially a picture of how likely the data is to be coming from a model with these specific parameter values. So the probability of seeing our data given a parameter value at every point on the horizontal axis. Any questions here? I mean, an even simpler way to set this up would be with just one data point. The most likely, the distribution of probabilities across the horizontal would give you essentially an estimate exactly at the y value that you picked. The most likely beta 0, the most likely average for a single data point is just going to be that data point. The middle of that distribution will be exactly your average. Here, we're just doing that 3 times in a row. I'm just multiplying those things together. Probabilities are multiplicative, and so we multiply them together. The probability of seeing 3 things in a row is the probability of each one multiplied by the next, if they're independent. You could make this more complicated if you like, by assuming like autocorrelation. You can build all of that into this model. But here we're just going to assume that the observations are independent from each other. Okay, I'm taking this as no questions. Okay, so what happens here is we have an estimated value of 0 for beta 0 of 1. And let's just check this. So what I'm going to do is run optimize, minimize scalar. So this is, the negative of the likelihood function. So because we're minimizing, we need the negative. You could rewrite this. I think this is sometimes a little more complicated than it needs to be. You can just rewrite a negative function, which I'm going to show you some examples of that later. And then just minimize that directly without needing a lambda function. And actually, should we do that? Let's say def negative example likelihood. And this is going to take in beta 0. And then this is just going to return negative of example likelihood. And then all we have to do here is just write in negative example likelihood. And I think that'll run. I don't really like lambda functions for some reason. Okay. So this is the the maximization. We've minimized the negative. And the actual height of the value is this thing. So we're dealing with very small values, right? Like it's just the height of the function, and because it's 3 of them, we're multiplying them together. Everything becomes very small. Any questions here? My econometrics professor, amazing guy, he'd be like doing all this amazing stuff on the chalkboard. Back then it was chalk. He'd like whip around, look at us, be like, any questions? Any questions? And then go right back. It's like, that was about the speed it would go. I was never brave enough to interrupt him. So that's the basic idea. We have this product, which is the density, and you can extend this to any arbitrary number of observations. Every time we add a new observation, we need to model where it's coming from. If these are IID from some underlying distribution that we've pre-specified, we just don't know what the parameters. This is just a product. And that product looks like this. So if these are independent and we're drawing from the same distribution, this is how we define our likelihood function. It's just the probability of seeing the first one given our data from our underlying distribution times the probability of seeing the second one given our parameter values from some underlying distribution. And then we just continue multiplying by these probabilities. Because each one of these probabilities is less than 1, the larger our data, the more unlikely any one of these outcomes will be. So the likelihood will be smaller when we have more data. This is not a deep insight. It's just if there's more data, there's more ways our data can go. Okay, any questions here? Kind of 2 problems here. First one, if we were to try to estimate this with a computer, because these are multiplicative, these values get very, very small, and computers, I'm going to show you later if we get to the example, you can actually run into like estimation issues when the errors get really, really small. So there are better ways of handling this to try to get around the fact that this is the probabilities are so small. The second thing is, I don't know. If you look at this and you try to take a derivative of a product, so the first derivative of the likelihood function with respect to one of the parameters, like theta 1, for example, derivatives of products they can be very gross. You could probably do it, but it'd be very challenging to do. What we're going to try to do is find the maximum value. And if we do this, we can do this analytically for some problems. And if we have a multiplicative likelihood function, this gets ugly. So these are kind of our 2 problems. And we're going to try to fix both of these problems with a simple transformation. Insert Shia LaBeouf transformer joke. Thank you. I'm here all afternoon. So what we're going to do is rely on this idea of a monotonic transformation. I'm sorry, I'm still stuck on Shia LaBeouf. Essentially, if you have an optimizer for one function that maximizes that function f, and then you take a transformation g of f of x, that optimizer will also be an optimizer for the composed function, so long as g is strictly monotonic or strictly increasing. I think you did this in intermediate micro sometimes, right? Like you can, you know, I think with utility functions, you sometimes like will do a log transformation and then you maximize the log. It's sort of a similar idea. So this is just a picture here. If I transform, so in yellow I have g of f of x. If I transform f of x using g of f of x, and an example here is a log, then, and I'm actually doing this, so this is the log. The maximizer, or the minimizer in this case, for f of x is the minimizer for g of f of x. This is the trick we're going to use to get ourselves out of this product problem. Okay, so the actual values are different, right? The evaluation of g of f of x will of course be different than f of x, but the optimizer will be the same. Okay, so nice. So that's the basic idea. I think something you all are pretty familiar with. We're just going to apply that idea to the product. If we take a log of the product, this fixes two things for us, or it fixes the core problem. Log is fine because it's strictly increasing on 0 to infinity, and because what we're giving the log function is a set of probabilities, it is coming from 0 to infinity. So this is going to be fine. This is the math for the log likelihood function. We're going to use little l to denote the log likely. We have theta and then we have y. So this is just the log outside of the product. So we have the product of all of our probabilities, which the product of all the probabilities, the log of a product is the sum of the logs. So, you know, the log of A times B is equal to the log of A plus the log of B. And this is the property we're going to rely on. We're taking a log of a bunch of probabilities multiplied together, and then that just becomes the sum of the logs. Okay, any questions here? All right, so I'm going to run this. This is just the log likelihood function, and this is what it looks like. This is just log likelihood. I'm just using the log normal PDF. So this is essentially pre-baking in the log. And then I'm giving the same data set we were working with before. So this is 1 minus beta 0, and then -1 minus beta 0, and then 3 minus beta 0. And this turns out to give us exactly the same output. So the last time we estimated that we've maximized our likelihood at beta 0. The same thing is happening here. The difference, though, is the log likelihood gives us a different log likelihood. And that's simply due to the fact that we're taking a log. Okay. But you can just take the exponential, so raise the log likelihood to e, and that's going to give you the same value. So this is just comparing those two. Okay, so y'all want to be more specific? You want to do some math? We'll do maybe I'll bring the enthusiasm today. It's a Monday. I woke up a little sleepy, so I see you. Not projecting, just, you know. We're just going to walk through a couple examples. This first one is just with a normal distribution. So this is like the same setup we had before. We're just going to work this through just very directly. Sometimes we can do this analytically, and that's what I'm going to show you a couple of times here, just to get a sense and a feel for what's going on. But then we're going to construct a log likelihood function and then run that through an optimizer to verify that the optimizer solution is the same as our analytical solutions. So that when we go to a bigger problem, we have some confidence that what we're doing is correct. Okay, so this is the procedure. What we're going to do is just take a first derivative of our log likelihood function with respect to the parameter that we're particularly interested in. So in this case, our single parameter is beta 0. And the log likelihood function is just the sum over the logs of the individual probabilities. We've specified that we believe our data is coming from a normal distribution. We just don't know where it's centered, which looks like this. So first derivative of each of the individual summed values, right? This is the summation. We bring the derivative inside the summation, gives us the sum of the slopes of each of these things. This is, let's see. So using the chain rule, the derivative of this thing is equal to the negative of the first derivative on top divided by the thing itself on bottom. So this is just using the chain rule. Then we can do this on the board if you like, but essentially this is just the derivative of the log. We have it's just 1 over the value on the inside, so log of x. The derivative of log of x is 1 over x. But then we have to multiply by the derivative of the inside. So this is 1 over chi, or phi. 1 over phi as a function of yi minus beta 0. But then we have to multiply by the derivative of the inside. So the derivative of phi is just phi evaluated at yi minus beta 0. But then the last thing we have to do using the chain rule is just the derivative of the inside of phi with respect to beta 0, which is just negative 1. So that's where this thing comes from. Any questions here? So then all we have to do is, so we're, this is the first derivative. This is our first order condition would just be setting this equal to 0. But we can actually be even more specific. The derivative of phi with respect to anything is the derivative of this. So phi prime is just, I really don't want to walk through this. I wrote it out in the notes so we don't have to talk through this derivative. You can follow every step. It essentially boils down to the derivative of e to a negative x. So you can walk through each of these steps. But it turns out, with the standard properties of the derivative of e to the x, that you sort of like remain, what is left over still includes e to the x. And that happens here too. So what happens is we're left with negative phi of z, which is the original function itself, times negative z. Okay, so this is really nice. We can use this to plug in for, so up above we had found this thing. We can just use the derivative of phi to plug in for the derivative of phi in that function, which comes out to be this thing. And here you can see we have a bunch of cancellations, namely that phi canceled with phi. So these two things cancel top and bottom. And all we're left with is this, which turns out to be a really nice first derivative, or first order condition. and I mean, this looks almost identical to OLS. So we have yi minus beta 0, sum over all of our observations is equal to 0. If you do a bit of rearranging here, so you can pull beta 0 out, it shows up, I mean, the way I think about this is as a sum of all of these things. So it's, you know, y1 minus beta 0 plus y2 minus beta 0. So there are n beta 0s. So we have the sum of yi's is equal to n beta 0. And then we just divide by n, which gives us this thing. Okay. If I were constructing a maximizer for the likelihood function, I would probably pick this thing. Like, without doing any work, what would I expect? It would be exactly this. It would just be, let's pick a distribution centered on the average of our data, which is exactly equal to OLS. What we did with the example we just worked through was say that we knew what sigma was. We said it was equal to 1. But if we didn't, we'd have to perform 2 first order conditions. The first one for beta 0, the second one for sigma. The steps would look identical. We get a first order condition like this, which gives us, you know, an estimate for beta 0 and for sigma. I wrote down 3 questions you might have about this as it relates to OLS. The first one is, how does this differ from OLS? We've walked through like a similarly structured kind of setup, maximum likelihood, just setting up the probabilities of all these things, and then we maximize the thing. How does that compare to a different approach where we don't come in with a particular structure on the data generating process, and then we minimize the sum of squared errors to give us our estimates? How do those two things compare? Well, it turns out the averages are the same. The OLS estimates for the variance are this thing. So it's so I guess the notation here is a little bit funny because I have this this one is squared and this one is not. But if you squared the sigma from MLE, the only real difference is that OLS has 1 over n minus 1, where MLE has 1 over n. So they're very similar, but just this one is, we have a smaller value in the denominator. So, so this is going to be a little bigger. Okay, any questions here? Are either of the estimates biased? Well, the MLE estimate for the average is unbiased, but our MLE for the standard deviation is biased downward slightly. So we've essentially, I mean, we know OLS is blue, so so it's unbiased. MLE is slightly downward biasing the standard deviation and the variance. So we're sort of underestimating the true standard deviation. Are these estimates consistent? Yes, both of them are consistent. So as n is going to infinity, we go to the truth with both models. So asymptotically, they're identical. Okay. It's just the reason that happens for MLE is because in the limit, as n goes to infinity, the standard deviation goes to the same answer that OLS gives us. Okay, any questions here? So this is really nice. We just set up a sort of a separate way of conceptualizing how we would go about estimating our parameters. The reason we're sort of doing this at a high level is there are lots of ways of thinking about how we construct our models, and that's kind of the main point of going deeper than OLS. There are reasons to think more critically about how we construct and estimate our models, and MLE is a common one we use. Okay, so we did all of this stuff. We derived this model analytically. We constructed the first order conditions. But let's actually try to estimate this using a larger sample. So the last like empirical example we used was with 3 observations. Let's actually run this with a lot of observations. Let's use a sample size of 1,000. The reason we check our analytical models against our empirical models or our simulated models like this is just to confirm that what we're doing is correct. So what I'm going to do is just collect 1,000 observations drawn from a normal distribution with a mean of 3 and then a standard deviation of 2. So that looks like this. What I'm printing out here are the sample statistics. So this is the average of y and then the standard deviation of y. And this, of course, is with a degree of freedom of 1. You could pull that out if you wish. Okay. So the next thing we're going to do is define a function that calculates the log likelihood. And all this is doing is just going through and constructing a log PDF. So I'm plugging each one of my y values into a log PDF. I'm centering this on some theta. So this is one of the inputs into the model. So this is essentially like my betas. We don't know what they are, so we're going to use them as inputs into the function. So if y going into some distribution, which we haven't specified. And then all I'm going to do is just sum them all up. So because these are log normal it's a log normal distribution. This is a log likelihood function, and we can just sum them together. Okay, and then I'm going to take the negative of this thing. So this is negative log likelihood, and then I'm going to minimize it. So this is just optimize.minimize, and then I'm giving it the negative. We're going to give it these 2 parameter values. So these are our starting values, our guess. You could maybe start at a more sophisticated place using the sample parameters. And then I'm going to use this fancy method. What this is doing, this is Newton-Raphson, but because we're dealing with logs, sometimes the basic Newton-Raphson will not converge. I learned this through trial and error that we need to use the log Newton-Raphson. I would run this a couple of times, and I would end up with non-convergence. So what I did is I added the log version. So that's L dash Newton-Raphson. This is the fancy version of Newton-Raphson. So I came to this through trial and error. And then what we want are some bounds. I don't need any bounds on the mean, but the standard deviation must be positive. So what I'm imposing is no upper limit on the standard deviation, but I'm requiring that it not be negative. So this is just going to be slightly positive. This is essentially just an increment above 0. And then I'm going to run this. It's going to print out the estimates and give us some nice results. Look at those nice results. So that looks like this. So the estimate for the mean is this thing. The estimate for the standard deviation is this. And then you can plug in the log likelihood into the maximum likelihood estimation. This also prints out the convergence. So MLE.success. But the main thing to realize here is the estimate is very similar to the mean. In fact, these are the same. So it turns out in this very simple case where all we're trying to estimate is the mean, we get exactly the mean through this process. I think in terms of compelling results, this is not one of them. But what this is doing is confirming that the model we've constructed, we've defined a likelihood function, taken the log of it, and then minimized it, minimize its negative. We get the average. We can also look at the standard deviation. And you'll see these are nearly identical as well. They're off by like a rounding error. But this is also nice to confirm. Part of what's happening here is we have a really large sample size. So the issues of the asymptotics, the consistency of the standard deviation sort of don't appear here. Okay, any questions? Okay, so the basic idea is we set up the likelihood function, we take the log of it, and that's the thing we specify. The reason we can do this is because we're predefining where the data comes from. And that's sort of the almost like the inverse starting place of OLS. So we're near the end of class. I just want to show you a few things here. Our estimates of our parameters, in this case we have 2. We can think about sort of slicing them just to get a picture. There's like this manifold over 2 dimensions, which is the sort of like estimator over the 2 parameters we're estimating. What we can do is slice both of them at the estimated value. So we're going to take a slice along one direction, and then we'll take a slice along the other, just to get a sense of what we're doing. So this is what we call the concentrated log likelihood function. It's we call this the concentrated log likelihood function. We're just holding the other parameter constant. And if we had more than 2 parameters, we would be holding all of the others constant. And then I'm just plotting a couple of points on the horizontal axis. So the vertical axis here is the log likelihood. The horizontal axis are different like beta parameters. And then I'm just holding the standard deviation constant and plotting these. And you can see this is really close to our estimated beta 0 of around 3. Okay, no surprise there. And then this is a picture of the concentrated log likelihood function over thetas. This looks a little bit different, but the main idea is the same. What the minimizer did is try to find the maximum, or the maximizer found the maximum because we took the negative. And this is all sort of conditional on the beta. But we did both of these things at the same time. We're optimizing over a 2-dimensional surface. Okay. Any questions about that? Let's see if we can get through one more example, and then we'll pick this up next class. Okay. This is This is slightly more dangerous. I'm always tempted to misspell Poisson. Watching a scary show over the weekend is poison involved. So we're just going to walk through a more complicated version of MLE. We're going to use Poisson in the example, the estimation example we'll do next class. But essentially, so this is the probability density function for Poisson. So each data point is a random count, k. So we're essentially just trying to think about the probabilities over counts. So we should call this, so this is the density function. This is just some nice little notation here. We're going to use the subscripts ki a little later. But this is just, I mean, it's a weird looking function, but this just allows us to sort of normalize the probabilities of different counts. I'll show you a figure of what this looks like in a second. You all familiar with Poisson? Have you seen it before? I think to say you're familiar with Poisson, that's not something I usually hear from people. Like I've worked with this for, I don't know, like a decade, but I'd not say I'm like particularly familiar with Poisson. It's a weird one. So let's go through and set up the maximum likelihood for this thing. So we're going to say we have a bunch of draws, n of them, which is our sample. They're all IID coming from the same underlying distribution. The reason IID matters is because that allows us to multiply the probabilities together. The independence of the IID gives us the ability to do the multiplication. The identically distributed part of IID tells us that the lambdas are all the same and the shapes are all the same. So these are all the same lambdas, but we have different observations. So let me just walk you through the log likelihood. What this is doing, the log likelihood is just, again, this is the sum over the logs of each of the separate I observations probability functions. So we have this thing, and this is the probability mass function for the I. So this is just the same thing here, except we're subbing in ki in for k. We have lambda to the ki times e to the negative lambda, and then this is all over the factorial of ki. So remember, ki is a count, so it's an integer, a positive integer, or non-negative integer. This thing, the log of that whole thing, using the same property of logs, allows us to expand this product, or this log, into this sum of the different values. So this is just an expansion of the logs. So the log of lambda to the ki is just the log of lambda times ki. And then the log of e to the negative lambda is just negative lambda. And then the log of 1 over k factorial is just the negative of the log of k factorial. Okay, so now that we've, first step is define the likelihood function. The second is take the log of it. And then the third step is to take the derivative with respect to each of the parameters we're interested in. So in this case, the only parameter is lambda. So we just take the first derivative with respect to lambda, and that gives us this thing. Amazingly, a lot of this falls out. So the factorials are all gone because there's no lambda. So this is just the derivative of this thing, ki times the log of lambda with respect to lambda is just ki over lambda. And then this thing is just -1. So this is just the sum over all of the ki's over lambda minus 1, but n times. So that just becomes n. So this is outside of the summation. Any questions here? So this can become our first order condition. So we set this equal to 0 and then solve, which gives us, so this, we're just moving n to the other side. Here we're going to pull lambda out. So 1 over lambda is the same for each of the summed values. So we can pull our lambda out. And then we just rearrange that to give us this. So our estimated lambda is just 1 over n times the sum of the ki's, which is just our average k. Okay, so again, with the MLE, we get the mean exactly of the Poisson distribution. This is not always going to be the case, but it is in this case. Okay, let's just plot a few things and then I'll send you out the door. So the first thing is just we're going to collect 500 observations from a Poisson distribution with a lambda of 2.5. And then I'm going to define a Poisson log likelihood, which is just the exact same thing. So this is, we're going to sum over each of the Poisson log PMFs. So I'm putting in the lambda value, and then we're going to submit the entire data set, the Poisson data. We're leaving lambda as the parameter, so we can optimize over it. And then this is just the negative. When I run it, the true lambda is 2.5. The analytical estimate is the average, right? So we just walked through all of this math to give us this thing. So our analytical estimate for lambda is just the average of the k's, which we can see directly. But then I've also defined the log likelihood function and estimated it analytically, and I get essentially exactly the same thing, off by just a tiny increment. So what does this tell us? Well, just like with the normal distribution, we can estimate single parameters using an analytical approach, or we can use the numerical approach that we've been developing. This is, again, a very simple example. What we're going to do next class is work on a couple of more complicated examples. So we're going to start on Thursday with this multinomial. And then we're going to actually go out into the world and estimate a 42 parameter model, which should be fun. Y'all hyped? Okay, nice seeing you all. I'll see you on Thursday. I'll be in my office from 1 to 3. Love to see all of you there. But if I don't see all of you, I'd love to see each of you, or any of you. It's so nice out. Well, it's warm outside. I think it's cloudy.